Ladies and gentlemen, come gather around, come gather around, come gather around. Today, we're talking camshafts. Huh? Everything you need to know in a nutshell, in a convenient sort of way. Let's go! And if you're a keyboard warrior who's just itching to tear a strip off of me in the comments about how I glossed over the important details of camshafts, you need to keep in mind, I am a high school mechanics teacher teaching high school kids enough about camshafts that they can kind of understand what's going on. If that's not acceptable to you, you might not be my target audience. Nevertheless, I appreciate that you're here. Let's have a go. So this video is a companion to my high school level 3 auto mechanics program where we talk about engine modifications and vehicle modifications. You're doing engine performance and you probably came to the spot in the booklet where we talk about camshafts, and I start to try to talk to you and explain to you lift, duration, overlap, lobe separation angle, and the things that are particular to camshafts. The camshaft is the magic of your engine. The magic of the camshaft affects the breathing of the engine and more so where it makes power and how you want it to make power. You can make it peaky, you can make it a broad torque curve, you can make it more grunt for towing, you can make it more horsepower for a muscle car or racing, and everything in between. So you kind of want to pick, what am I going to do with my car, and then find a camshaft that does that. Way back in level 1, we pulled out this cutaway of a Briggs & Stratton or Tecumseh engine, and we talked about how all of this works. We got the camshaft is down inside there. We've got some tappets or lifters. We got the valve springs. We got the valves. This is a side valve engine or a flathead engine, and this kind of got phased out by the 50s by most manufacturers, and we went to an overhead valve design. So in level 1, we showed the operation of the engine, and we had the piston at top dead center. Well, let's back up a second. Okay, top dead center, top dead center of the crankshaft rotation, intake valve starts. And you would have assumed in level 1 that the intake valve suddenly opens when the piston goes down, suddenly closes when the piston's at the bottom, compression, power, and then suddenly we open the exhaust valve, send it out the exhaust, and then suddenly close it. And that isn't entirely true. We're going to get to that. What we're looking at in level 3 is engine performance, and the single most limiting factor of the breathing of this engine. We want it easy for air and fuel to get in, and we want it easy for exhaust to get out. The single most restricting part of this whole thing is these valves. If we can make it easier for the air to get around these valves into here and out of the valves and out, we can make more power with this, and that's a good way to go. However, there's limitations. I can only make this valve so big before it gets in the way of this one. I can only make this one so big. At some point, these two valves are going to be too close together and we have issues. We also have physical limitations with how big of a valve we can fit inside this valve, or inside this cylinder head. On an overhead valve engine, we have 2 valves or 4 valves or how many ever valves here. We got valves in here above the piston. And again, you can only get so big before the valves touch each other or touch the cylinder walls. If you have the valves too close to the cylinder walls, you get shrouding. And that's where you can't actually use that part of the breathing of the valve because the cylinder's right there and kind of plugging it off. So you don't actually want them too big. You want them big, but not too big. Since we can't really change these a whole lot, and while we can go bigger, where do you go once they're as big as you can go? We could try lifting these higher. So maybe this thing lifts, look like about 5 millimeters, 4 or 5 millimeters. If I could make this open more, then it would be a bigger space around here and I can get more airflow through it. How far the valve opens is called lift. So this is valve lift. Generally speaking, valve lift is awesome just about everywhere. There are some restrictions to that. There's some limitations to that. So we'd like to have the valves open instantly like this and close instantly. That way we can have maximum amount of flow for the entire duration that that valve is open. From here to here, maximum amount of flow. That's ideal, that's optimal. However, physics rears its ugly head yet again. Momentum can be a good thing where something in motion wants to stay in motion, and we can use that. But when the valves are closed, an object at rest wants to stay at rest. And so to take a valve that's closed and make it frickin' open instantly is really hard on the metal and the physics of the whole thing. We can't quickly, rapidly, instantly open it. And if you could, the closer you get to an instant opening, the harder it is on the materials and the mechanisms in your valve train. And then you start to break things. Life in the automotive world is like that. If you want maximum power, you have to compromise longevity. If you want it to last a long time, you have to give up some power. Every decision in life, everything you want has a price. And it's like power and longevity. You have to decide where you want to dance with the devil on that one. So while I can't do this instantly, what I can do is, if this is where I want the valve to be open, I can try to open it like this, and I can close it like this. And the opening ramp and the closing ramp might be symmetrical, they might be different. Doesn't really matter, that's not the point of this video. But we need to progressively open it and then smoothly and progressively close it. If it opens too instantly, the valve may want to keep moving, it might want to stay in motion. That's called valve float. That's Mother Nature's rev limiter. We also need to close it slow enough that the spring can control that. If the cam lets the valve close too quickly, the valve might bounce a little bit on the seat. There's challenges, so we need to be, as aggressive as we can get away with without compromising too much life. So that's how we deal with lift. The overall opening to the closing of the valve is called duration. And duration, it plays a pretty big role in shaping the power of your engine. Well, let's look at the duration, but we're going to go backwards a little bit, and we're going to start from the exhaust side and work our way back to the inside intake stroke, because that's going to make a bit more sense to us. Okay, so we have the intake valve, we're sucking in air and fuel, we compress it, we ignite it, and then watch what's happening here. This piston is here, and that valve right there, that valve is starting to open right now. We're not at the bottom of our travel yet. That's the bottom of our travel right there. So we go down a good, 3/8 of an inch of this piston, which is now opening the valve. The valve is opening before we get to the bottom. Why are we opening it before we get to the bottom? Good question. When combustion happens, it's pushing the piston down, but once this piston gets, 2/3 of the way down the hole, combustion's kind of, the force is really diminished a lot, and we're not really applying a whole bunch of pressure in here. But we need to get this cylinder empty so we can fill it with fresh air and fuel. We don't want any exhaust to be stuck in the cylinder. So if we can get a head start opening this, then even while it's still under some high pressure, that high pressure will find its way out through the valve, and then we'll push the rest of it out with a piston. So we can open this valve earlier and earlier and earlier and get a head start trying to empty things out of here. So if I'm going down here for exhaust, if I can get that thing open early and quickly, I can get this thing fully open by the time we're pushing the exhaust out. And look at what's happening here. The piston's coming up. Okay, and that valve is opening. The piston is not fully at the top, and this guy is actually not closed anymore. We're starting to open that. That one's not fully closed, this one's not fully open, but this is still open, and this is open. Not much, but it is open. The action of this valve and the action of this valve are currently overlapping. And overlapping is a good thing right here. So why do we want some overlap in here? If you ever siphoned gasoline, and I won't ask when you've done that, but if you've ever siphoned gasoline, you've got like a hose and a bucket. If you've ever siphoned something, you probably know about having a hose that fits into here, into a bucket, and there it goes down near the bottom, and then you get your hose going wherever you want it to go, and you know that if you apply a vacuum onto the end of this hose and suck some of the liquid up, the liquid's going to come up here and nose over here, and as long as your output is lower than where the liquid is, it will continue to exit. And what it is so the exiting liquid over here has mass, and that mass gets moving because you applied a vacuum to this, and that exiting mass is going here, and it's going to create a low pressure or a vacuum behind it and start to pull the other liquid out through the hose, and it'll slowly drain the whole thing. It's miraculous and it's wonderful. It's one of the 7 wonders of the universe, siphoning. And we do the same sort of thing with our engine. When the exhaust valve is open and the exhaust is exiting the cylinder, so this exiting exhaust has mass, and that mass has momentum, and so that exiting momentum of the mass will create like a low pressure in the in the port and the chamber and help to pull out the last of the exhaust from the cylinder. And I want every little bit coming out of there, and so in essence, I'm siphoning that cylinder clean. In the automotive world, we call it scavenging. I like to use the word siphoning for the sake of students, because most of them have siphoned before, for reasons I don't want to get into. Let's look at the intake side. Let's say the piston has started going down and the intake valve is open, and we have air and fuel filling the cylinder. Okay, so we've got a section of air and fuel coming into the cylinder this way, and the piston is drawing it in. When the piston gets to the very, very bottom of the cylinder, that air and fuel has mass. That mass has momentum, and it's in motion, and it wants to stay in motion, and it will continue to fill that cylinder even if the piston is heading up. We get to the bottom of the cylinder, and the piston stops. And like I'm doing this, I'm trying to find that spot where it stops. Piston stops there. This valve is very definitely open. This is not fully closed with the piston at the bottom. Let's back up. Piston's coming down. It's at the bottom. Now it's coming up. Holy crap, look at that. The piston's coming up, and now the valve is closing. Back up to our idea on momentum. If we have this piston coming down the hole, we've got air coming through here. We have volume, we have mass of air and fuel coming into the cylinder. And this is the single biggest restriction. So if I can have the valve stay open later, I can have that mass continue, because Newton's law of motion, an object in motion wants to stay in motion. It wants to keep filling that cylinder to the point that even though this piston is coming up, that momentum will still be filling the cylinder while the piston is starting to compress it. Okay, so to maximize this and milk that momentum as much as I can, I'm going to close that valve a lot later than you would expect. In level 1, you assume it just kind of shuts off at the bottom, but in real life it doesn't. So I'm going to close this intake valve after bottom dead center. Okay, it could be, I don't know, 20, 30 degrees afterwards of rotation. It could be pretty significant. And if you have the whole length of the intake system tuned with the right size runners and the right length of runners, you can get some pretty good cylinder filling properties. Same thing with the exhaust system. If you have the right size diameter tubing and the right length of pipe on there, you can have some pretty good cylinder extraction or scavenging or siphoning. And they all work together. The exhaust system is every bit as important as the intake system, and you need them both to be working together. You'll find on the interwebs, people will say, you gotta have some back pressure to make some power, and that's hogwash. No engine needs back pressure any more than you need to be a little bit constipated to work at your best. If you've ever been constipated, you know you're not gonna bring in fuel. You don't need to go for pizza if you ain't pooped in 3 days, okay? So we don't want any back pressure, but what we do want is a reasonable size tube and a reasonable length that works for that scavenging siphoning action. If you've ever siphoned with a hose that's like way too big, you know it doesn't work. It has to be a small enough one that actually works for what you're siphoning. And this is the same kind of thing. It really is all related, and it's kind of important. At high RPMs, like a racing motor, this incoming air charge can ram itself into the cylinder pretty effectively, and it's moving, and an object in motion wants to stay in motion. Why don't we just let it get through there a little bit more? So for a performance engine, I might close that intake valve significantly after bottom dead center. So I might go quite a ways after bottom dead center. And to get a head start on this one, I might open that exhaust valve significantly before bottom dead center, because this is moving. If I close this significantly after top dead center and open this one significantly before top dead center, I can have both of these valves open at the same time and use that exiting exhaust to help pull the air and fuel in. So when the exhaust is coming out of here and it's exiting, how much of this piston is moving? There's not a whole lot of stuff moving. It's coming up here and completely stopping. And if this piston is stopping, how much exhaust do you think is going to be pushed out anymore? How much intake do you think is going to want to be drawn into the cylinder? Not much, because the motion has stopped. Once this guy, like here, I'm moving the crankshaft like a little bit, now the piston starts to go down, and now we've got the valve open. So what we're actually doing by having both of these open just a little bit, is the exiting exhaust can now try to siphon the air and fuel into the cylinder while the stuff is exiting. It's like we're siphoning a tank of gas, and we emptied the cylinder, and now this thing is empty, and we open this guy, and now we're sucking air and fuel out as well. And every engine pretty much has some overlap. Different levels of overlap can change the power curve, but you want to have some so that that exiting exhaust can help get a head start in starting to fill the cylinder. And what you want to have happen is this guy closes, and he's now closed. Like, it didn't move very much, and he's suddenly closed. Open, he's closed. So it's like that much distance. It's not a lot of distance here. As soon as that thing closes, now we have already some air and fuel in the cylinder. It's already started to move, and it's getting some mass and some momentum happening there, and we can suck in the rest of the air and the fuel. There's a bit of a cost here, okay? So what I'm showing is I'm going to be opening the valves earlier and closing them later, and opening the valves earlier and closing them later. And at some point, those two valves, the valve operations can overlap each other. At some point, these are going to overlap so much that at low speeds, air and fuel is going to go right out the exhaust. And you could have the excitement of having some of that exhaust come right back into the cylinder, even back into the intake manifold. And you can imagine if I'm not getting full cylinder filling because some of the air and fuel is left, or I'm not getting cylinder filling because some of the exhaust is still in there, this thing's not going to run very nice at low speeds. And that is the music of my people. The sound of an engine with a large valve duration, where the valves are open a long time, the sound of that on an engine and the overlap of those two valves is the music of my people. Let me play you the music of my people. Let's go back to the previous style of drawing that I did, where we're looking at the duration of the valve event and the lift that the valve does. And we're really going to look at this part right in the middle. So we have the intake valve opens, closes. We've got the exhaust valve opens, closes. And the exhaust valve is closing just as the intake valve is opening. The overlap of these two is where the exiting exhaust helps to draw in the fresh incoming air fuel charge. Now, we did talk about just a moment ago that the longer I can keep the intake valve open, I can fill that cylinder more at high speed. And the earlier I open it, I can get more of a head start with the exiting exhaust pulling in air and fuel, again at high speed. So the intake, new intake, might look like this. And why not go for more lift while we're at it? I mean, really. Maybe this is like your stock cam and that's a performance cam. Let's do the same with the exhaust. So now we got the exhaust valve opening earlier and closing a lot later, and we have the intake valve opening a lot earlier and closing a lot later. I hope I got that right. Now our overlap is going to be increased. So now we have a lot more overlap. We have an increased probability at low speeds of having the intake get drawn into the exhaust and exit through the exhaust as well, or have the exhaust that exited the engine get sucked back into the engine because the piston's going down and it may suck exhaust back into the cylinder. Good for lowering your NOx emissions. At high speeds, this will be magical, but at low speeds, not awesome. Let's see how that looks on cam lobes. So here would be your lobes on a camshaft. The exhaust would come around, do its opening and closing, and just as the exhaust closes, the intake starts to open, and it does its closing event as well. Overlap is directly related to the duration of the cam lobes. Bigger cam lobes, we're going to have more and more overlap. A lot of overlap really destroys your low-end performance and idle and even drivability around town. So there's ways that camshaft manufacturers mess with that to try and give you the power you want at high speed, but make it livable at lower speeds. And that's the angle between these lobes. The angle between the lobes is your lobe separation angle. And I like messing with that. And all of this is all related. If you're changing one thing, you're changing a bunch of other things too. So you kind of want to wrap your head around all of it. Don't get fixated on one part of it. And I tend to get fixated on things, but here's what's going on. If you have a really aggressive camshaft and you have a lot of overlap, you're going to kill the low speed power. So many manufacturers will build a pretty aggressive cam but change the lobe separation angle. So if it's a little bit wider, you're going to be reducing that overlap, because this lobe might come over here and that lobe might come over there, and we can reduce the overlap from New England. That overlap can make it a little bit different. So a common lobe separation angle for camshafts is around 110 degrees, maybe 112 degrees. I've seen some that are 114 degrees. The wider it is, the more it kind of restores what you're losing by having a big camshaft in there. If you're willing to sacrifice a little bit of drivability, tightening these even more can be pretty cool. One of my heroes in the automotive engineering world is David Vizard, and he talks a fair bit at length about this, has calculations for whatever your engine is, and comes up with a lobe separation angle that may work well for your engine. And he tends to like camshafts that have a little bit tighter lobe separation in the ballpark of 108 degrees or so lobe separation angle. 108 degree lobe separation is going to be tighter. It would increase your overlap. However, if you pick a reasonable cam for the RPM you want to run at, and then tighten up the lobe separation to get a bit more overlap, you can have an engine that makes power where you want it, but is really efficient in the mid-range and builds torque. So a lot of old school RV cams and towing cams were relatively small in duration, but had a pretty tight lobe separation angle to give it some really good torque right in the middle there. And that's a handy thing to do. You're gonna find people on the interweb who are like, oh, that's crazy, don't do this is the way to go. Don't do, all the cam manufacturers do this. And David Vizard is saying, none of the cam manufacturers do this, but this is what makes power. First time I played with this was Isky cams. They had Isky mega cams that had 108 lobe separation, and Isky was like the only cam manufacturer that was doing this, and Isky cams made power. Factory cams are going to be up here because they want quality idle, smooth, fuel economy, emissions. They're not as keen on ultimate power. Brian Tooley Racing is famous for doing truck cams, and they've got like a stage 1 truck cam, a stage 2 truck cam, and then they came up with a cam a couple years ago that's like, this is it. Of all of our research, of all our dyno tests, of all of our everything, this is the truck cam to be all truck cams. And they came up with a cam called Truck Norris. And I was interested in the specs to know what did they do with Truck Norris that makes it the awesomest truck cam. And the dyno tests have shown, yeah, it brings you torque all over the place. It's definitely a torque cam. And finally the specs started showing up on the interweb, and what did they do significantly? It's a smaller duration that fits a reasonable RPM range for your truck, but they have a lobe separation angle of 107. And when I saw the specs at that at 107, I'm like, well, yeah, that makes sense to me. They tighten it up, they get some overlap, and it builds torque. Of course, that's what they would do. All the truck and RV and towing cams had that kind of thing back in the day. So that makes sense to me, absolutely. One of the ways to look at the effects of camshafts on the power that your car makes is like this. Let's say this is your typical horsepower and torque curve, and horsepower and torque are mathematically connected. They're a relationship of each other. So let's just kind of look at it this way. If I increase the duration of a camshaft so they open early and close late, regardless of lobe separation, but let's say we make a bigger and bigger and bigger camshaft, it will take from the bottom end and put it up on the top end, and it may look a little more like this. So it's going to lose here and then probably start to gain here. And you may make a whole lot more power up here than you lose, but you can't get this without losing that. There is no camshaft that gives you more down here. It just doesn't happen. So you're always going to lose. You can lose a little bit, but you'll gain a little bit more, or you can lose a lot and gain a lot more. How would that affect the torque? Torque is going to be similar to the same kind of thing because they are related. So this will probably be less, but it may start to build up here and carry further. And these are just, it's a graph. If you can just see the idea that you're losing some and gaining some, that's what happens. If you go for, and I'll do this in a different color, let's say we pick a camshaft that has tighter lobe separation, okay? Not huge duration that ends up with overlap. Let's have a sensible camshaft that happens to have more overlap. When you have tighter lobe separations, typically your torque will take a little bit away from here and it'll gain a whole lot more
but probably nose over it. And you may lose some of your absolute top end. You definitely will lose a little bit of bottom end, but it's going to give you scads more power here in the middle. Eric Weingartner did a cam shootout with a whole bunch of people who built cams, made cams, chose cams, and sent them all to him. And he did a whole whack of dyno test with all of them. And the top 3 cams had lobe separations that were 108 degrees. There were some that were 108 degrees that didn't rate in the top 10. Some were pretty bad. But again, your duration and the overlap and lobe separation angle, they're related. You need to make sure you're looking at the whole package, not just one thing. I like these, but whatever. Let's take a look at duration one more time so we can understand some of the specifications that people use with duration. When we're measuring the duration on a camshaft, most manufacturers don't go from the instant it opens to the instant it closes, because then you're going to get a false reading. I can have a cam that opens very gradually and not very far, and closes very gradually. And it'll be nice to the valve train, but the effective open part of the valve is not going to be very much. So I can't really compare that cam. Chevy used to have a cam back in the 60s called the 350 horse 327 cam, and it was the mainstay. I think it's the 141 cam from GM, and it was the mainstay for, everybody put on the 350 horse 327 cam in everything. And it had very large duration, but it opened very gently. And by modern standards, that is an antiquated old school cam. We get more aggressive by tightening up the duration so it actually makes power in a useful range, but open the valves a lot more aggressively. So where we compare camshafts today is at a certain amount of valve lift. Forgive my crudity over there. All cam manufacturers today have a standard unit of measurement for duration, and it's going to be at 50 thousandths of valve lift. So they open the intake valve 50, and then from there measure the duration until it's 50 thousandths away from being closed. And then you have a more standard, realistic way of looking and comparing cams. They can still change the aggressiveness in here, but it's less dramatic of a change here. So when you're looking at picking a camshaft and where you want to run it, you're going to be looking at 0.50 thousandths of lift. Ballpark numbers of duration. My 61 Chevy Apache has a stock 6 liter with a stock camshaft in it. And it is 196 degrees of duration intake and 207 degrees of duration of exhaust. And it's on 116 degree lobe separation angle. And from the factory standpoint, this would give you a reasonably low speed torque, not high RPM power. With this, it's going to be relatively smooth idle, good emissions, good fuel economy, and that's what it's supposed to do. I put a turbo on it, but that's a different topic. This thing kind of peaks out at about 5,500 RPM or so. I think the rev limit is somewhere around there. If I wanted to get a bit more aggressively, a popular size camshaft for an LS is going to be in the ballpark of 225, maybe 235 degrees for intake and or exhaust. And this kind of a camshaft will probably rev to 6,500 or more quite nicely. If you want it to rev higher, you need to increase the duration. This will be fun on a street vehicle, but the bigger the camshaft is, the more it's going to cost you at low speed. And by low speed, we're talking maybe 2,500? Maybe 2,500 RPM, maybe 3,000 RPM. So below that, you'll probably lose some torque, which, for a Camaro, who cares? But if you've got a truck, that may be a bit more of a concern. I really want to put a camshaft in this engine, but when I drove it around town, in town, it's driving along at 1,100 RPM. On the highway, I'm cruising at 2,200 RPM. I don't need a camshaft that's going to cost me power there just to get excitement here. And I haven't quite accepted what I want to give up. And that's just it. If you want high RPM power, you have to give up some low speed torque. If you want low speed torque, you have to give up some high RPM power. Changing the duration just moves the power curve. It takes and gives. But if you want everything, well, that's boost, and that's a different conversation. BTR's Truck Norris cam has an intake duration of it's under 220 degrees, and an exhaust duration that's somewhere in the 220s. They're not exactly revealing where. And that would give you a power curve would get you below 2,000 RPM and probably peak at about 6-ish. And that's not bad for a truck. That's not bad. Boy, I hope I can make this video short. So while there's a lot more to camshafts than just lift, duration, and overlap, this should give you a bit of a nutshell of kind of what we're talking about and how it affects things in the performance of your engine. There's black magic and voodoo in all this, there's science and physics, and there is a metric crap ton of opinion out there that you need to wade through as you're trying to figure out what camshaft you want to get. So there it is. As always, thanks for watching, take care, and we will see you again.